Good morning, students. In the last lecture we have seen the simple pendulum, and the motion of the simple pendulum is nothing but the linear SHM, that we proved that. So today we'll see the period of a pendulum, that is T, capital T, as the time period is given by 2 pi upon omega. So 2 pi, that omega, we know that omega is equal to this. In the previous lectures we have seen that F is equal to ma, that is by the Newton's law, and F is equal to kx, that is minus kx it is. So ma, so ff, so both are the forces, that's why we can write here ma is equal to kx, that is a by x is equal to k by m. And as we have this k by m, it is nothing but the angular frequency, that is the omega square. So that is, we can write instead of k by m, omega square is equal to a by x. That is, a is nothing but the acceleration and x is the displacement. That is, omega square is equal to acceleration per unit displacement. So here we use this value in this formula for the time period, that is t is equal to 2 pi upon omega. So it is 2 pi under root of acceleration per unit displacement. We have taken root as it is omega square is equal to a by x. Here is omega, that's why I have taken here root. So by equation 1, what is the equation 1? This was our equation 1. F is equal to minus mg x by L. So I have written this equation here again, and we have the formula F is equal to ma, that is by the Newton's law. So by these two equations, comparing these two equations, we can write ma is equal to minus mg into x upon L. So this will cancel, and we have a is equal to minus of g into x by L. That is again acceleration per unit displacement. If we take this x to this side, that is a by x, it is nothing but the acceleration per unit displacement. It is equal to g upon L. That is the length of the pendulum. That is in magnitude, if we take the magnitude only, that is g by L. Therefore, the equation 2 becomes, what was our equation number 2? That is t is equal to 2 pi upon this acceleration per unit displacement. Here we can write a by x also. That is, we can write here, this is nothing but a by x. So here the equation 2, it becomes equal to t is equal to 2 pi. Instead of a by x, we got the value as g by L, that is the gravitational acceleration by length of the pendulum. So 2 pi upon g by L, that is, it becomes under root of L by g. This is nothing but the period of the simple pendulum. So we can have the formula for the frequency as, I'll show you. This is the formula for the frequency, that is n is equal to 1 upon t. Right? The frequency is nothing but a reciprocal of the time period. So that is, we can write frequency as 1 upon 2 pi root of g by L. So from this formula for from the motion of the simple pendulum, the formula for the time period for the simple pendulum, we have some assumptions. That is, some assumptions are there, and that is, we can call it as the laws of the simple pendulum. The first law is what? The amplitude of oscillation is very small. As we have seen in this diagram, yesterday we have seen that in the simple pendulum, this is bob, and this theta, it should be very small, that is, this theta should be less than 10 degree, and the motion should be like this. Right? So these are the extreme positions of the bob. So bob will go to and fro about this mean position. So amplitude of oscillation, this amplitude, it should be very small. If the amplitude is small, this amplitude, that is the this angle is small, then we can say the amplitude of oscillation is small. And if it is small, then only this motion of the bob, it will appear as the linear SHM. It will appear to be happen along the straight line or along the linear path, better word. So this will be the linear SHM if this theta it is small. Then second assumption is the length of the string is large, right? This L should be large for the motion to be linear SHM. If this L is small, then what happened? It will form the arc-like structure. So the length of the string, it should be large. This is the second assumption, or we can say that it is the second law of the simple pendulum, for the oscillation of the simple pendulum. The third one is, during oscillation, bob moves along a single vertical plane. It is moving along the single vertical plane in this to and fro motion. The next is, I have explained it already, that n, that is nothing but a frequency, the number of oscillations completed in the 1 second, or we can say in the time period t, that is nothing but a frequency. N is equal to 1 upon t. So we have the formula for frequency as 1 upon 2 pi under root of g by L. Here this g is nothing but the gravitational acceleration, and this L is nothing but the length of the string of the pendulum. The next is the fourth one. The period of simple pendulum is directly proportional to the square root of its length. The period of that, for the formula for the period, it is equal to t is equal to 1 upon 2 pi under root of L upon G. So the formula for the period, sorry, this is the formula for the frequency. We'll write the formula for period. So this period, it is given by t is equal to 2 pi. It is root of L upon G. That means the period of the simple pendulum is directly proportional to the square root of its length. Right? If this 2 pi it is constant, and if G is constant, then we can say that t is directly proportional to root of L. Then next is number 5. The period of simple pendulum is inversely proportional to square root of acceleration due to gravity, that is G. If these things keep constant, that is, if the length of the simple pendulum, that is the length of the string of the pendulum, it is constant, this is also already constant, then we can say this t is inversely proportional to G, that is the gravitational acceleration. Then the next number is number 6. The period of simple pendulum does not depend on its mass. So in the formula we can see, in the period of the simple pendulum, it is only the length and the gravitational acceleration is considered. So we can say the mass, that that the mass of the bob, it doesn't affect the period of the simple pendulum. So the period of the simple pendulum, it does not depend on its it does not depend on the mass. So it is independent of the mass of the bob. The next is the period of the simple pendulum does not depend on its amplitude for small amplitude theta. That is this theta. If it is small, then the period of the simple pendulum, that is the t, it is independent of the amplitude, that is theta, and it applied for the small amplitudes only. So this is about the laws of the simple pendulum. Then next we'll see the seconds pendulum. What is the seconds pendulum? It is seconds pendulum is nothing but a simple pendulum, but whose period is of 2 seconds. So we'll see the definition. A simple pendulum whose period is of 2 seconds, it is called the seconds pendulum. Again the same assembly is there, that a bob is there, that bob is moving to and fro about the mean position, and this is the amplitude of oscillation, that is theta. Then only the difference is what? It is a simple pendulum, but its period is of 2 seconds. That is called the seconds pendulum. So here, as we know, the period of the simple pendulum, it is given by t is equal to 2 pi under root of L upon G. So for the seconds pendulum, we can write that it is this period, it is equal to 2 seconds. So we'll write, instead of this t, we'll write here 2. 2 is equal to 2 pi under root of Ls upon G. So here, this is the formula. Here this Ls is nothing but the length of the seconds pendulum. This length, this Ls. So this Ls, it is nothing but the length of the seconds pendulum, that is whose period is 2 seconds. So again squaring this to both the sides, that is it is 4 is equal to 4 pi. It will come out of root, that is Ls upon G. 4 will it cancel, and we have Ls is equal to G upon pi square. So this is nothing but the length of the seconds pendulum. This is the formula for the length of the seconds pendulum. So this is about the simple pendulum, laws of simple pendulum, and the seconds pendulum. So next we'll see the angular SHM in the next lecture.